The Western and Eastern Snake River Plain by Shane Lynch, Cynthia Mouzis, and Michael Orcutt. In what surely conjures images of William Clark and Meriwether Lewis braving the early 19th century Wild West Columbia River tributary, otherwise, at first look, appears to be, well, rather drab and boring. But wait, what is it about this supposed old Yellowstone hotspot? What is beneath this banal, sweeping, plain facade? Or is it just a giant smiley face? Surely to the layman, it looks to be a topographical area of minimal consequence, but intriguing in that it stretches the entire southern expanse of Idaho. All that aside, you will come to appreciate that it is arguably one of the most impressive of Idaho's geologic provinces, due not only to its vast reach, but its formation, its resources, and its idiosyncrasies. So what comprises the western and eastern Snake River Plain? Well, for starters, its rock types can be broken down threefold. First off, the majority of the Snake River Plain is covered with quaternary to tertiary igneous rocks of primarily basaltic, but also rhyolitic and andesitic or intermediate composition rocks. For example, the Big Southern Butte and the remaining handful of rhyolite domes in the eastern Snake River Plain are actually younger than the predominant basalt field in which it is embedded. The Bruneau River basalts show how some of the Snake River Plain sediments have covered some of the surface-based basalt in the central Snake River Plain, while the Great Rift of the eastern Snake River Plain shows how basalt flows also remain quite visible in other areas of the geologic province. Secondly, we see quaternary sediments deposited from various processes. Predominantly, quaternary sediments come from alluvial deposits and associated stream terraces with existing rivers, but also massive flooding deposits, discussed later, glacial deposits, and also windblown sediments or dunes account for other loose sediment makeup. Bruneau Dunes State Park in the central Snake River Plain is a great example of wind-deposited quaternary sediments. Thirdly, found predominantly in the western Snake River Plain, there are slightly older sedimentary rocks, aging back to the early Tertiary period or Eocene epoch, with other sediment and grus stratigraphy mixed in or interconnected with less dominant basalt forming from basin and range processes. Lacustrine lake deposits from the ancient Lake Idaho and older stream terrace deposits. When overlaying these three rock types, a sense of how the Snake River Plain formed starts to take some shape. Copious amounts of lava from Snake River lavas in the east and Columbia River lavas in the west were deposited with predominantly layer depositing of sediments via various and sundry processes. But before moving on to the actual formation and deformation history of the Snake River Plain, it is important to understand that gravity anomaly, magnetic correlations, along with and relative to the Snake River Plain's axis, additionally also flood deposit markers from the massive Lake Bonneville flood. Fourth, radiometric potassium argon and argon to argon dating, and lastly stratigraphic correlations of the Cenozoic layer beneath the dominant quaternary basalts and rhyolites all combined to aid in dating the Snake River Plain's age. So what has acted on this region to deform it? Or has it deformed at all? Of the structural deformation present in the Snake River Plain, faults are the more developed story to be told, while folding takes a back seat. The western Snake River Plain is a graben, or an area of rifting, where the center moves down relative to what it is bounded by, caused by normal faulting due to extension and tensional stresses. Side note, there is some debate about the western Snake River Plain as a graben because there is no evidence of older underlying Cenozoic sediments that match up to those that are found in the south and north of the Snake River Plain. In the eastern Snake River Plain, there are minimal influencing faults governing current topography. That said, there are a few isolated non-active faults indicating volcanically caused rift zones and underlying calderas. Additionally, there is some gravitational anomaly and topographical evidence of a fault on the northwest boundary of the eastern Snake River Plain. Now that we have identified existing features, let's look at how the Snake River Plain took shape.
The Snake River Plain began forming only about 16 million years ago. The first part of this development didn't even occur in the region we know as the Snake River Plain. It began in the Owyhee Plateau area, the border between Idaho, Oregon, and Nevada. You can see this border between those three states in the pictures displayed. This is where the Yellowstone hotspot and huge volcanism began. Less than 1 million years ago, the North American plateaus we can see in the diagram on the left of the screen moved southwestward, cutting through southern Idaho over the hotspot that is currently located beneath the Yellowstone caldera. We can see this location on the right diagram represented by a dark black bold line. The Earth's crust was pulled apart during this move, and a large topographic depression formed. This topographic depression became the Western Snake River Plain. It began as a rift valley that filled as lava moves upwards onto the surface through crustal fractures. You can see the uplifted lavas in the middle of this diagram. This area held a giant lake for a long time as well, which geologists have named Lake Idaho. In the formation of the Snake River Plain, there was first an eruption of high-temperature, high-volume rhyolite from magmas rich in silica and alkali elements. There was an eruption of basalt, which is richer in iron and magnesium, that came from the Earth's mantle. Geologists have found that both types of eruptions occurred in the eastern Snake River Plain, which makes the origins of the eastern and western portions distinctly different. In the eastern portion, there are massive craters, up to several hundred square miles in area, commonly known as calderas. Calderas formed by rhyolitic lava flows are found along the margins of the eastern Snake River Plain, while basaltic lava flows overlay them. You can see some of these calderas in the diagram with the Yellowstone hotspot on the very right. There are also 5 major rhyolite domes present on the eastern portion, displayed from left to right on the screen: Big Southern Butte, Cedar Butte, Middle Butte, Unnamed Butte, and East Butte. If you reference the key, you can see the layers of basalt lava flows on top of a layer of rhyolite. There were many events that helped in the landscape of the Snake River Plain, but the final event that impacted it was the Bonneville Flood that occurred about 17,500 years ago, modifying the landscape in many interesting ways. The heavy flow of water eroded out and enlarged the Snake River Canyon, and excavated little plunge pools while tearing out blocks of basalt in the process. These blocks of basalt, larger than 10 feet across, traveled down the flood channel, became rounded, and accumulated into large bars where the water velocity was lower. These large basalt boulders are now located in a field near Hagerman. Now let's discuss some interesting and very important facts about the Snake River Plain. Some layered basalt lava flows and some sediment composes the eastern Snake River Plain aquifer, which is the single most important aquifer in Idaho. As you can see in the cross-section, the thickness of basalt is over 5,000 feet, so groundwater flows easily and more rapidly in the upper 500 feet, the most productive portion of the aquifer, according to geologists. This is due to the interconnected pore spaces. The upper 500 feet is said to store groundwater at 200 to 300 million acre-feet, approximately the size of Lake Erie. There has been increased groundwater pumping, which has had a major effect in the decline of spring discharge and groundwater levels. In the diagram, you can see the substantial decline in levels between 1975 and 1995. Although the aquifer is extremely important to this region, there is also the potential hazard due to the presence of volcanic activity, especially in the eastern portion of the Snake River Plain. Although the threat potential is very low, there is located the Craters of the Moon volcanic field, formed by 8 eruptive episodes between 15,000 and 2,000 years ago. This field contains 55 cones with lava flows and 14 fissures.